so periodic trends, we talked a little bit and briefly introduced the idea of the Z effective, the effective nuclear charge, written like this, ZEFF in the little subscript. Now, this is the overall net positive charge that is attracting a particular electron. This is one of the reasons why we know there are different energy levels amongst the principal quantum numbers. S's are lower than P's, P's are lower in energy than D's, and D's are lower in energy than F's. It's because of this effective nuclear charge and the overall idea of shielding electrons. We're going to have different energy levels. Now, core electrons effectively shield the outermost electrons. And so core electrons are not what we're going to be looking at for effective nuclear charge. The particular electron that we want to focus on are those valence electrons, because those are the ones that go into reactivity. Can we calculate the effective field of the nucleus on those electrons and understand why some are more reactive than others? So the outermost electrons in the valence shell do not shield one another. They will only be shielded by the core. And what that means by being shielded is the idea that when we look at the reactivity, the valence electrons are being on the outside, they do not feel as many protons in the nucleus. Again, nuclear charge, there's protons in the nucleus, and those protons are attracted to electrons. Opposites attract. So when we get into that idea of protons being attracted to electrons, the valence electrons don't feel as much attraction to the protons because of the shielding that is seen from the core electrons. Now, overall, what a periodic trend will be a statement that states what happens. It doesn't explain why. We're going to explain why with our quantum mechanics and the theory behind it. But here's the periodic trend, our first one. The effective nuclear charge increases as you go across a periodic table and stays the same as you descend down a column. So from left to right on the periodic table, Z effective increases. We'll be able to see why. But as we go down a group or a family, the Z effective stays the same. So now we see in this nucleus, we're dealing with a +3 nucleus, so that means we're dealing with lithium. You can do this with any sort of atom that you want. Now, lithium has an electron configuration. We'll do the full one, 1s2, 2s1. What we want to do is figure out, what is this guy feeling? Is he attracted to the nucleus? Is he not really attracted to the nucleus? What's happening to him? How much of the nucleus is he actually attracted to? And the answer here is the Z effective. What we need in order to calculate the Z effective is the actual number of shielding electrons and the nuclear charge. So how many protons minus the number of core electrons. That's what we need. Z, right here, is the nuclear charge. That's the count of protons. S is the number of electrons specifically in the core, and that's how we get our Z effective calculation. So for lithium, the lithium Z effective is 3 plus 3 minus 2. Which means the outermost electrons are feeling about 1 proton. It's not a perfect calculation, but it's effective. Now, let's take another atom in that same family. Let's go to potassium. Potassium has an electron configuration. We'll do the noble gas configuration. Argon, 4s1. Now, argon is 18 electrons. Plus that extra 1, potassium has 19 electrons total. So the Z effective here, if potassium is atomic number 19, it has 19 protons in the nucleus and 18 core plus 1 on the Z effective. Same exact Z effective. Even though it's a larger atom, the outermost electrons feel about the same number of protons, no matter if we're dealing with lithium or potassium. That tells us that the reactivity of those outer electrons for lithium and potassium is effectively the same. They're feeling the same number of protons, they're still slightly attracted, but not really, really attracted. Second trend is atomic radii and how does it actually affect our size of the atom. This is the wrong chart. There it is. Radii of atoms. Let's first look at the gray circles here. The radii of atoms, as we move across left to right on the periodic table, across a row, we picked out here group 1, 2, and 3 just to show the similarities amongst these, but it would extend all the way across to group 7A or 17, the halogens. And what do we notice? 152, 112, 85. These are in picometers. So the size of the atom decreases as we go from left to right. Well, what is causing that? The Z effective. As the Z effective increases, that literally means the electrons on the outermost shell are feeling more of the protons in the nucleus and therefore being held tighter. So as we think about the Z effective, yes, we're increasing the number of proton count. Yes, we're increasing the number of electron count, but the actual attraction between those protons and those electrons, the Z effective, is increasing as we go across the row. And so therefore, the size of the atom decreases from left to right. As we go down a group or down a family, what is important to note is that size is increasing. Well, Z effective does not change going down a group, but what does change is the principal quantum number N is increasing. We are actually physically putting these valence electrons in a totally different shell. And so as N, the principal quantum number, increases, we see the size of the atom increases. We will see this repeated over the course of the next few periodic trends. As we go across the row, Z effective increases, so electrons are held tighter. As we go down a group, the N value, the principal quantum number, is increasing, so electrons are further away from the nucleus. Now, notice the red dots now in comparison to the gray. If we look at the relationship here, lithium to lithium plus 1 cation, or beryllium to beryllium plus 2 cation, cations are always smaller than their parent atom. And the reason for that is because when a cation forms, they are losing electrons. So we are looking at losing the valence electrons. So there are less electrons to hold in the atom, and so therefore the size decreases. We're removing those electrons from the outermost N, and so we are decreasing the actual distance away from the new outermost electrons. So cations will always be smaller than their parent atom or element. Here again, we see the other half of the periodic table, group 6A and 7A, or 16 and 17. As we again move from left to right on the periodic table, we see that size decreases because the Z effective is increasing. Electrons are being held tighter, and therefore more attraction. Being held tighter, therefore they are closer to the nucleus. Not very much, a couple of picometers, but still important. Get all of them down in there. Now again, looking at the relationship between an anion and its parent, anions will always be larger than their parent. And that's because, again, we're putting more electrons in the outermost shell, taking up more space, having to share that Z effective a little bit more. Their parent being the neutral element. Excellent. Periodic trend number 3, ionization energy. This is a potential energy. This is looking at the minimum energy needed to remove an electron from an atom or ion in the gas phase. Notice how it's specific to removing an atom. So I'll rewrite this reaction. Some sort of atom in the gas phase going to become a cation, specifically a cation. This is what we call ionization energy. If it's the first electron removed, we call it ionization energy 1. Now, we can remove more electrons. We can say that M+1 cation in the gas phase can go to become an M+2 cation in the gas phase. Notice how both of these are losing electrons. Which one or what number we're on, that ionization energy is always going to be positive. Energy is required to remove an electron. Why is it required? Because when we think about removing an electron, that electron is attracted to the nucleus. It's like a magnet on the fridge. In order for that magnet to be pulled away from the refrigerator, we have to put energy in, which is endothermic. It requires energy. Now, notice here on the same first and second ionization energies, they actually put the electron there as a product, as if it's being pulled away from the metal itself. Excellent. Now, everything has an ionization energy, but what I like to look at in this chart, as we move from left to right on the periodic table, from lithium all the way up to neon, or sodium all the way up to argon, these are moving left to right across the periodic table. What we notice is that ionization energies increase. Across that periodic table. Why? Why would it be harder to remove an electron? Why would it cost more money to remove an electron? And that is because the Z effective is increasing. Those electrons, as we move across from left to right across the period, the Z effective is increasing, which means those electrons are getting held tighter and tighter and tighter. The atom is getting smaller and smaller and smaller. Those outermost electrons do not want to leave. It costs a ridiculous amount of money or energy, to remove a fluorine electron to become fluorine +1. This is why we would never see nonmetals form cations. They just don't. Nonmetals don't like to form cations. Now, as we go down a group, ionization energy decreases down a family. Or a group. Why? Because N is increasing. Way back, we talked about playing Red Rover. And remember, if we think about playing Red Rover, we want to be held as tight as possible when we play that so that our neighbors can't crash through and break apart our arms. Now, as the atom gets bigger and bigger and bigger and bigger, yeah, the Z effective is staying constant, but the actual energy of those electrons in the outermost orbital is increasing because of N. So yes, it's feeling the same attraction to the nucleus as we go down a group, but the actual size of the atom is important to discuss. And so why we see the ionization energy decrease, it doesn't cost as much to remove an electron from potassium as it does from lithium, because potassium is a much bigger atom. Here are some generic, another way that the book shows that. Highest ionization energy here, lowest ionization energy down here. So we see this generic trend of increasing up a group and across from left to right. Again, for the same reasons as before, either the Z effective or the principal quantum number. Now, trends in succession, the second and third and fourth ionization energies. It depends on the number of valence electrons. So pull out here nitrogen versus oxygen. Nitrogen has its valence right here, 5 electrons. Oxygen has 6 electrons. And what we're really wanting to specifically look at is how many in the P's. 3 P's. Write it the other way. P3 and P4. So what we notice for this is we're going to have a very specific difference between nitrogen's 5th ionization energy and 6th ionization energy, because we can remove 5, but we definitely don't want to go into the core. For oxygen, we'll see a big difference between the 6th ionization energy and the 7th ionization energy, because again, we can remove the valence, but we don't want to get into the core. We can see that with sodium and magnesium. Sodium has 1 valence electron. So it's a very small number for its first ionization energy, but start to think about removing a second one. These are core electrons. We never want to remove those. Magnesium has 2 valence electrons. So we see a first ionization energy that's small and the second one that's a little bit bigger, but look at this huge jump now between the second and the third. We don't want to go into the third for magnesium because we only had 2 valence. We're gonna start to dip into the core. So there will be always a large increase when the core electrons are starting to be removed. So valence electrons have relatively low ionization energies. The biggest jump happens when you have removed all the valence and you're trying to remove a core electron. We can see this step ladder as we move across the periodic table. This is the 3rd row, starting with sodium and then magnesium, moving all the way across. Looking at this step ladder, we can see that once you've removed all of the valence, sodium has 1 valence, magnesium has 2 valence, aluminum 3. What we notice is that there is the biggest jump on 1 more than its valence. So sodium has 1 valence, its biggest jump comes at the 2nd ionization energy. Chlorine has 7 valence. The biggest jump is going to come over here at ionization 8. Big, huge. Don't even try. Excellent.